Hello everyone and welcome to the fifth topic in the SS2 first term physics curriculum. Now in this topic we're going to be looking at linear momentum. Now under this topic here are the different subheadings we're going to be considering. Firstly, we'll look at the concept of impulse. I will be able to define what impulse is and then apply its equation to solve problems. I will also look at the concept of momentum, that is, be able to define momentum, get the equation for momentum, and apply it to solve problems. Then we'll look at the Newton's first law of motion, also known as the law of inertia. We'll be able to state the law and interpret the law, that is, tell the meaning of this law and how it can be applied. Now, we'll also look at the second law of motion, that is the Newton's second law of motion, which is where we usually derive the equation F equals ma. So we'll state the law, we'll derive the equation, and then we apply that equation to solve multiple problems. Now, after that, we then look at the Newton's third law of motion. I will state the law and we also interpret the law and also mention how it can be applied, that is, in different ways in which it is applied. We look at relatable examples around us where the Newton's third law of motion is applied. Then when we are done with that, we then look at collision and type of collision. Now we have to look at what collision means in physics and the different type of collisions we have. That is the elastic and inelastic. We explain what each of them mean and how they are applied in physics. After that, we then look at the application of the Newton's law and the conservation of momentum law. Now there's Newton's law. There's law of conservation of momentum. We look at these two laws and then we look at how they are applied. And then once we are done with that, we then look at the inertial mass. That is, we should be able to define what inertial mass is. Now, you are more conversant with what is known as mass, but we look at what inertial mass is. Then we look at what weight is compared to that. After what we are looking there basically is we'll be able to define what the weight of a body is. Then we look at what happens to the weight of a body when it is in a lift. And we're going to consider about 3 to 4 scenarios. The first scenario being when you are in a lift and the lift is moving upward, what happens to the weight of your body? Now, when you are in the same lift and the lift is moving downward, there's a change there. So we look at what happens in that scenario. Then we also look at what happens when the lift is falling freely under gravity. That is, if someone is in a lift and then it cuts and then the lift begins to fall freely under gravity, what will happen to the weight of the body in that lift? And then we look at satellites and weightlessness to close the entire topic. So you agree with me that it's a very broad topic, but it is very essential to every physics student to be able to understand all of these and also apply them, especially to solve problems. Because majority of the exams you're going to be facing include questions that are from this topic, so it is very important. This is why you do not want to miss it. So please ensure that you are subscribed to the channel. You can do this by clicking the subscribe button, and you can also hit the notification bell icon so that every time we put out a new video, you will always be notified. And please, we are asking you to also assist us to reach many more students like you who need helpful videos like this. Like I mentioned, what we are looking at here is very important. So please ensure that you share the video. All you need to do is click the share button and then they would also receive it and be able to locate the channel. So please click the share button and encourage them to also like and share the videos. Now, one more thing you can always do to ensure that your learning is complete is that whenever you have questions based on what we are doing, or perhaps even during your study time, you come across something that is a bit challenging and you would like our help with that, we encourage you to please put your questions in the comment section and we promise to attend to all of your questions, thereby bringing more understanding to you so that you get to understand the topic in more detail. So please ensure that you drop your comment and we will always make sure that we respond to all of your comments. Thank you so much for that. Now, if you're ready, let's dive into the world of linear momentum. Let us look at the concept of impulse. Now, being that you are already at this level in physics, it means the word force is not new to you. Now, you know that agent that causes an object to move or to continue moving at the velocity it is, or to change direction, or to even stop, is what we know as force. Now, when this force acts on a particle, right, within that time frame with which it is acting, there is something that is felt there. Now, that is called in physics is impulse. Okay, it's basically, simply put, it is the effect of a force acting on an object within a short time. Now, let me explain this. Consider that you have an item, say a ball, right? If the ball is stationary, for it to move, it requires a force to be acted upon it, right? So now, how do you act that force on it? It's either you kick the ball, you throw the ball, or any other means, right? Now, we are used to kicking the ball like in the game soccer or what is known as football. Now, when you kick that football, it's going to start moving. So within that short time that force acts on it, it causes it to move away or to be thrown away. Now, you would still have short time there, and the force acting, it is the product of those two things that give us what is known as impulse. So if you're going to define impulse in physics, you will say it is the effect of force acting on an object or a particle within a short time. Another way to put it is to say it is the product of the average force acting on a particle and the time during which the force acts. Now, let's put these two definitions down so that we will always recall it. Now, remember, the first one I said is that impulse is the effect of a force acting on a particle within a short time. Another way to say it is what we said when we said impulse is the product of the average force. The average force acting on a particle and the time period within which it is felt. Okay, so that is when you look at the product of the average force and the time during which the force acts on that object, then what you are considering there is the impulse. So if we're going to say this, impulse is often denoted I, okay, and it is the product of force F and time T. So let's note that where I is impulse, okay, F is the force, and T is time. Now, this is the part where I mentioned that it is not limited to this equation that you see here. You already know that force can have different equations to represent it. There is force equals mass times acceleration. There is force equals mass times velocity squared over radius. That is when you are looking at force in a circular motion. Okay, centripetal force, for example, where you have mv squared over r. All of these still mean force. So no matter how you represent force, as long as you are multiplying force by time, what you are getting there is impulse. Let us look at a question on this so that we can apply this equation to find the impulse. To apply the equation of impulse, let's look at this question. It says a stationary ball is hit by an average force of 100 newtons for 0.13 seconds. That is 0.13 of a second. What is the impulse experienced by the ball? Now, to solve this, okay, all you need to do is recall that impulse is force multiplied by time, right? So that is the impulse experienced by the ball here is going to be the product of the force. Now, what is the force in this question? We're told that the average force is what? 100 newtons. And this is what we're going to multiply by the time. Now, the time for which the force was experienced is 0.13 of a second. So 0.13 seconds. Okay, now when you multiply this, it means the impulse experienced is going to be 13 Newton second. Now, two things we get from this question. First off, as regards this ball, the impulse experienced is 13 Newton seconds. And then the second thing we have learned from this question is that the unit of impulse is Newton second. Newton second. So whenever you're asked to also derive the unit for things like this, you can apply the equations to get the unit. So since it is force is measured in newtons, multiplied by time, which is in second, that gives you Newton seconds. So as regards this question, the solution is 13 Newton seconds. Now let's go to the concept of momentum. When we want to define what momentum is, now we often say it is the amount of motion that an object has. Now, because we define it this way, many people tend to think that momentum only refers to an object that is in motion, and it is not present for objects that are stationary. And when you look at it, it may look like that, but it is not exactly what has just been said. Now, consider in the case of an object that is stationary, and then it experiences an impulse. Now, remember we said impulse is the product of the average force and the time during which that force acts on an object. So now when you hit that object, it experiences that impulse, which causes it to move, right? Now, at that point when it begins to move, we say it has gained momentum. Does that mean it does not have momentum at the initial? So you see, here's the thing. At the beginning of this statement, we looked at an object that is stationary. At that point, it is not moving, so the velocity is zero. So at that point, it has zero momentum. Now, zero momentum still means momentum. It's just that it does not have any value. It is zero, null. Okay? But the moment you hit it, it gains momentum. The same thing can happen to an object that is already moving, right? Now, when the object is already moving and then it receives impact from another force, that is, another impulse is experienced, it will cause it to change direction or speed up. So as a result, what happens there? You see that it gains more momentum. So it has an initial momentum and then a final momentum. So if we want to define momentum based on this, we would then say momentum is the product of the mass of an object and its velocity. But I'm going to put those two definitions down just in case. So whichever one you would like to use, depending on the kind of questions you'll be facing. You know, there are some questions you will face that will require you to define momentum from the first perspective, which is the amount of motion that an object has. And then there are other kind of questions you would face that will require you to use the other definition, which is the product of the mass of an object and its velocity. So let's put both of them down. Momentum refers to the amount of motion of a particle. It is the product of mass and velocity of a particle. Now you can always use object in place of particle when you are writing your own definition. So it depends whether you are just looking at it from the aspect of an object or a particle. All of them are the same. Now, how do we then find the momentum of an object using this definition? Now, we state that momentum, often denoted P, equals mass times velocity. So that is P here denotes momentum. Okay, M here stands for mass. And then V stands for velocity. Now that we know the equation, let us apply it to solve question. In this question, we are asked to find the momentum of a boy of mass 40 kilograms running at 20 meters per second. So this 20 meters per second is the velocity of the boy, the speed of the boy, while the mass is 40 kilogram. So solution. We know that momentum P is given as mass times velocity. So the momentum therefore becomes 40 kilograms multiplied by 20 meters per second. Now we're going to get the momentum as well as also learn the unit of momentum. So the momentum of the boy is therefore 40 times 20, that will give us 800. Okay, and the unit is kilogram meter per second. So the unit of momentum is kilogram meter per second, and the solution to this question is 800 kilogram meter per second. As we continue in our study of linear momentum, this stop is very necessary, and where we look at Newton's first law of motion. Now, another name for this law is the Newton's law of inertia. Okay, so to understand this law, the first thing we have to look at is what inertia is. Now, inertia, okay, when we say inertia, it refers to the tendency for an object to want to continue doing what it is doing unless a force acts upon it. So, for example, if the object is stationary, it wants to remain stationary unless a force acts on that object. For example, you put a book on a table, it will always want to remain on that table unless you lift the book away, you push it away, or you drag it down. It will want to remain there. The same thing if an object is moving. It wants to continue moving in that same direction at the same speed unless a force acts on it. So that tendency for an object to always want to continue doing what it is doing presently is what we know as inertia. So let's put that down. This is the tendency of an object to remain stationary or continue moving at uniform velocity in the same direction unless acted upon by a force. Now, when we understand that every object wants to remain stationary or continue to move at the same velocity in the same direction unless they're acted upon by force, otherwise known as inertia, then we can understand what the Newton's first law of motion or the law of inertia clearly states. It is based on this. And what the law states that an object will remain stationary or continue to move in the same direction at constant speed unless acted upon by a force. Okay? So, let me explain this. Take for example, when you are sitting in a car, a fast moving car, say a Ferrari or a Bugatti, and then you suddenly speed forward. What do you observe happening to the driver and other people in the same car as the car immediately speeds forward? Now, you observe that the moment they begin to speed up, once it speeds forward, at that instant, the person in the car shoots backward. The car is moving forward, but the person shoots backward. The person is only saved by the seat there. If there wasn't a seat there, the person would hit the entire back of the car. Now, this is because that person or that object wants to remain stationary. But because a force now acts on it, forcing it to want to go forward, in that time, it will shoot back first before it is able to continue in that motion. Because it wants to remain there. Consider this. This is the person, this is the car. The car is moving forward. The person only remains where he is. But the car has moved forward, which is why the person shoots backward. The same thing happened while they are driving very fast. And then the driver immediately slams on the brake. What do you observe happening at that point? You see how the person shoots forward. Now, this is why cars are equipped with the seat belt as a safety precaution in that case. Because once you slam on the brake, because of this same law, the Newton's first law of motion or the Newton's law of inertia, the object, the person in that car will want to continue at that same speed that they are going. Imagine the speed of that car, that fast moving car, and then an object moving at that same speed. It's going to be very disastrous if the person moved away from his seat without something to restrict that motion. So you see, the object wants to continue moving at the same speed, okay? And then once you slam the brake, it will want to continue unless the force, which is the tension in that seat belt, is able to stop the person from moving forward, thereby stopping an accident. So now that we understand how inertia is, let us put the first law of motion or the law of inertia down. So I'll write that as Newton's law of inertia. Newton's law of inertia states that an object will remain stationary or continue moving at uniform velocity in the same direction unless acted on by a force. To further explain this, consider when you're riding a bicycle. Now, as you begin to pedal, the bicycle begins to gain speed, right? Now, it gets to some point, you stop pedaling. Now, when you stop pedaling that same bicycle, the bicycle does not immediately stop, right? It continues to move in the same direction and then will continue like that until eventually it comes to a stop. It first starts slowing down and then after a while, it stops. Now, you see here that when you stop applying force to make it move forward, it does not stop. Why? Because of inertia. It will want to continue moving the way it was moving while you were applying the force. Now, because of other forces such as friction and air resistance, this is why the bicycle eventually slows down and stops. That is, if you remove friction, if you remove air resistance, the bicycle will continue at that same speed in the same direction. I hope you understand the law now. So together, let us state Newton's first law of motion. So you say it states that an object will remain stationary or continue moving at uniform velocity in the same direction unless acted on by a force. While the Newton's first law of motion is able to tell us what force does to an object, it does not actually define force in detail. So what gives us an absolute unit for force is the second law of motion. Now, let me first try to make it as simple as possible before we state the law itself. You see, what this second law of motion is all about is that it is telling us that the harder you push something, the faster it is going to move. And that bigger objects require more force for them to move. Now, to explain this, if you kick a ball softly, it's only going to move slowly forward or slowly in the direction in which you have kicked it. Let me put it that way. Because it is always moving in the direction of the force applied. Okay? So if you kick it softly, it will move slowly in the direction in which you have kicked the ball. Now, if you kick the same ball harder, now it is going to move faster in the direction in which you have kicked it. So it is telling you that an object is going to move faster based on the amount of force that you impress upon it. Now, if you apply the same amount of kick to a heavy stone, you are not going to see the stone moving because that stone has more mass than the ball. So you see that heavier objects require even more force for them to be able to move. And that is basically what the Newton's second law of motion is trying to tell us. Now, if we are going to explain this in terms of how physics sees it, we will now state the second law of motion as that the change in momentum of an object is directly proportional to the force impressed upon it, and that it moves in the direction of the impressed force. Let's put that down. Newton's second law of motion states that the rate of change of momentum of an object is proportional to the impressed force, and the object moves in the direction of the force applied. Okay, now let's look at what is in this law and what is in what I have explained as the simple way of describing the second law of motion. Now you see here that the object is going to have what? A change of momentum. Now remember that when we were talking about momentum earlier, I said it describes how fast an object moves. Okay? Now, bring that into this law now. You see that the rate of change of momentum is proportional to the impressed force. What does that mean? When you apply little force, the object has little momentum, meaning that it does not move fast. Now, when you apply more force, the object is going to move faster. That is for the same object. Now, the same thing applies whether the object is of lesser mass or of higher mass. So, for an object with more mass, it means that you need even more force for it to have a considerable amount of momentum. Okay, so basically, if something is heavy, all you need to do is apply even more force if you want to make it to move. Okay, now what we're going to do is we're going to try to state this mathematically now and then derive an equation from the second law of motion. So you know the second law of motion. Let's now get an equation for that. That is, derive an equation for the law of motion, the second law of motion in this case. Okay, now the Newton's second law of motion stated that the rate of change of momentum is proportional to the force applied and it moves in the direction of the force. So we will say the law states that force is proportional to change in momentum. Momentum over time taken. Okay, now this is the rate of change of momentum and this is force. Now where force would be denoted with F, momentum, change in momentum, would be mv minus mu all over t. So note, m is mass, okay, v is final velocity, okay, u is initial velocity, and then t is time taken. Okay, now let's put all of this together. Now what that means is that we then say F is proportional to mv minus mu over t. Okay, now what does this mean? F therefore will equal, now when you change the proportional symbol to equality sign, you have to introduce a constant. So the constant will be constant k. So mv minus mu over t. Now one thing you must note here is that the unit for force is chosen in such a way that K equals 1. So if K is 1, we can then say F equals mv minus mu all divided by T. So from here we can say F equals, M is common here, so M, then we have V minus U over T. Okay? But you know that V minus U over T is acceleration. A. So therefore we can say F equals mass times acceleration. So you see that this equation, force equals mass times acceleration, comes from the second law of motion. But it all starts from stating the law that the rate of change of momentum is proportional to the force impressed and it moves in the direction of the force. Let's apply this to solve a couple of questions. This question requires us to apply the equation for the second law of motion. It says that an object of mass 40 kilograms will be accelerated at the rate of 5 meters per second squared when acted upon by a force of what magnitude? Then we have to find the magnitude of the force that will act on this object whose mass is 40 kilograms and then is accelerated at 5 meters per second squared as a result of the force impressed. So here's the solution. What we are given that the mass M is 40 kilograms, okay? And acceleration A is 5 meters per second squared. And then we are asked to find force F. And F equals mass times acceleration. Therefore, the force applied would be 40 kilograms multiplied by 5 meters per second squared. And this would give us, now 5 times 0, 0, 5 times 4 is 20, so we have 200 kilogram meter per second squared. Or better put, force equals 200 newtons. Okay, note, N implies newtons. Okay, which is the unit of force. So the solution to this question is 200 newtons. Let's solve two more questions on this equation. Let's take a look at this question. A ball of mass 0.5 kilograms moving at a velocity of 20 meters per second is suddenly hit by a force of 10 newtons for a time of 0.01 second. Now we have to find its new velocity. Okay? Now let's look at what we have. Now we are given that the mass of the ball, M, is 0.5 kilograms. Okay? The initial velocity, U, is 20 meters per second. We're given that the force applied, the new force applied is 10 newtons. Okay? And then the time period is 0.01 seconds. So we have to find V. Now what equation combines all of this? We have F equals mv minus mu over t, which you can write as Ft equals mv minus mu. And then when we write this, we can say Ft equals m into v minus u. It all depends on how you want to work with this. Okay? So, what we see here is that impulse can also be changed in momentum. This way, you can always use this equation whenever you have the impulse. Because this same question could be rewritten in such a way that you are given the impulse and then asked to find the new velocity. So, this is another equation for you to use in that case. But let's continue to solve this question by using this particular one. Now, we have the force. The force is given as 10 newtons. So, 10 multiplied by the time, 0.01. Okay? And this equals the mass, which is 0.5. Okay? Now, this would give us final velocity v is unknown minus u, initial velocity, 20. Remember, that's in meter per second. Okay, what does this mean? It means we have 10 over 100 equals, this is 1 over 2 into v minus 20. Okay, so let's cross multiply, because this is basically 10 here 1, 10 here 10. Now when you cross multiply, you have 2 over 10 equals v minus 20, which implies that we have 1 over 5 equals v minus 20. Okay, so from here you can now choose to go whichever route you find easier to solve with. Now I like working with linear equations, so I'm going to take this 5 here again and say 1 equals 5 into v minus 20, which implies that 1 equals 5v minus 5 times 20, that gives us 100. So from here we can now say 5v equals 1 plus 100. So which is what? 1 plus 100 will give you 101. So v therefore becomes 101 divided by 5. And then if you solve this, what do we have? 5 will go in 101. It will go 20 times. So remainder 1. And 1 over 5 would give you 0.2. So that will be 20.2. And velocity is measured in meter per second. So the solution to this question is 20.2 meter per second. Let's solve this question. We are told a body of mass 0.1 kilogram dropped from a height of 8 meters onto a hard floor, and then it bounces back to a height of 2 meters, and we have to calculate the change in momentum. And then if the body is in contact with the floor for just 0.1 second, what is the force exerted on the body? Now, if we are to analyze what we have here, let's take this as the body. Now, it's going to drop to the ground here. The distance here is 8 meters. And then upon hitting the ground, it bounces up 2 meters. Now, this will be the maximum height above ground on the return motion. Okay? So that means if we can find the momentum where it hits the ground, we can also find the momentum at maximum height at this point. And then we find the change of those two, the difference between those two. Now, here's something you must take note of. If we take this as a positive momentum when it is approaching the ground, that is when it is moving up, what we'll be having is negative momentum. So to solve those, we need velocity just before it hits the ground, and then velocity, okay, the initial velocity as it is going to this point here. So at this point, we take the velocity here to be 0. Okay? So if it is 0 at that point, we can then find the value of u, the initial velocity at this point, and then we find v for this one. So let's solve those. So we'll start by finding v just before it hits the ground. Now to find v, what do we have? We have that u is 0 because it is dropped and it falls freely under gravity. G is given as 10 meters per second squared, and then we are given h as 8 meters. So to solve this, we're going to apply the third motion under gravity, which says v squared equals u squared plus 2gh. Now we're using plus because the object is falling to the ground, of course. So at this point here, this tends to 0, so we can just say v squared equals 2gh. So v squared therefore becomes 2 times 10 times 8, which is 160. So v becomes square root of 160, and that will give us now square root of 160. That gives us 12.649 meters per second. Now let's find u. To find u for this second motion, we say at max height, v equals 0. So v squared, that is 0 squared, equals u 1 squared. Now it's going up, so it will be minus 2gh. Now what this means is that we have u1 squared equals 2gh. So, and that will give us 2 times 10 times, it moves up 2 meters. Okay, so let's take out this. Now what do we have? It means u1 squared therefore becomes 40. Okay, so if that is 40, it means u1 is square root of 40, and that will give us 6.324 meters per second. Now, if you recall something earlier, I mentioned that on the motion to the ground, we'll take that as positive momentum, and motion away from the ground, we'll take that as negative momentum. And change in momentum is supposed to be mv minus mu. Okay? The only thing is that what we have here is negative of this. So it means that our own change in momentum will now be mv minus mu. Okay, the negative of what we're going to get when we apply the negative velocity in this case. So what do we have there? That will mean mv plus mu. And that will give us m into v plus u, which means we have 0.1 into, now what is v? 12.649 plus u, 6.324. Now, when you multiply all of this, when you do all of this together, that is 12.649 plus 6.324. That will give you 18.973, and then we multiply that by 0.1. And all of it will give us 1.8973. Okay? And this is approximately 1.9. And the unit for momentum is kilogram meter per second. So now we have the change in momentum. What is next is to find the force. Now, force is supposed to be change in momentum over time. Okay? So that is, we have 1.9 divided by the time, which is 0.1. So the force applied therefore becomes, now this is 19 newtons. So by doing all of this, we've been able to solve this question. So what we've seen here is that the change in momentum is 1.9 kilogram meter per second, and then the force exerted on the body is 19 newtons. Don't forget, if you have any question on the Newton's second law of motion or any other thing that we've discussed in this video, please ensure that you put it in the comment section, and we'll definitely attend to all of your questions. Now let us consider the Newton's third law of motion. But before we do that, if you're yet to be subscribed to the channel, kindly take a moment of your time to click the subscribe button. It doesn't cost you a dime. All you have to do is click the button and you are subscribed to the channel. And you can also hit the notification bell icon so that every time we put out a new content, you will always be notified. Now, folks, we are also reaching out to you to please help us to reach many more students like you to get helpful content that we always release on this channel. Now, how you can help us achieve this is to always share our videos. So for every video you watch, please ensure that you click the share button. That way, every of your friends will also see the link and then be able to watch the video as well. And they too can be subscribed to the channel so that they can always get helpful content that we release here on the Oyalen channel. So let me tell you, thank you in advance for clicking the share button, for subscribing, and please don't forget, if at any point you have a question on what we are doing, or perhaps during your own study time, you came across something that you need some help with, please ensure that you drop the question in the comment section and we'll definitely attend to all of your questions. Now, to understand what the Newton's third law of motion says, don't forget that the first law is the law of inertia, which tells you that objects will always want to continue staying stationary or continue to move in the direction that they are already going at constant velocity unless they are acted upon by an external force. And then the second law tells you that the rate of change of momentum is directly proportional to the impressed force, and it moves in the direction of the force applied. Okay? Now, this third law is trying to remind us that forces always come in pairs. Now, this pair of force is what we call the action and reaction. Let me come again. Forces come in pairs, that is action and reaction. Now, let me explain this to you. Now, when you push an object with a force, now you will observe that on your hand you feel an impression of something pushing you backwards too, especially when you are trying to push a heavy object. Now, by the time you are pushing it forward, the force you are applying is going to make that object gain momentum and move in the direction of the force that you are applying. Now, the reverse of that is the weight of that object that you feel on the hand that you are using to push the object. It feels as though the object is resisting your push, that is, it is pushing you back. So you see, action makes it move forward. The reaction is what you feel. Now, another example of this is what happens when you jump. Say, for example, you are at the swimming pool and then you want to, show off, do your cannonball thing. And then the moment you jump from the edge of the pool, now there's something that happened there. The way you jump is what you consider here. When you want to jump, you push down on the ground. So when you push the ground reacts by pushing you up. So you press down, the ground presses you up. So that is what results in your jumping. And then you can then show off by somersaulting and then diving into the water. I hope you understand what I'm saying here. So you see, you applied a force, the action, and then whatever you applied it on is going to react. And what you see here is that reaction is equal and opposite. Okay? Now, this is what constitutes what we know as the third law of motion. Now, what does it say? It states that action and reaction are equal and opposite. Let's put that down. Newton's third law of motion states that action and reaction are equal and opposite. Another way to state this is, that is, to every action there is an equal and opposite reaction. Now, whichever way you state this, you are still correct. Whether you say that it states that action and reaction are equal and opposite, or you say that to every action there is an equal and opposite reaction, you are still saying the same thing. And you can also combine both of them as it has been done in this video. So now you see that every time a force is applied, the reverse always applies in the opposite direction of that force. That is what we mean by the reaction. So to every action, there is equal and opposite reaction. And that's the third law of motion. Let us look at the conservation of linear momentum. Now, this is a law which involves the momentum between colliding objects. So if you look at two objects moving at their own velocities and then they come in contact, that is, they collide with each other, something changes. Now, it's either they move apart from each other at different speed, they move in the same direction with the same speed. It all depends on the type of collision, however, which we are still going to look at. We're going to look at the elastic collision and inelastic collision. But before then, what does the law state as regarding conservation of linear momentum? Now, what it says is that when you have colliding objects in a closed or isolated system, the total momentum is conserved. Now, let's put that down. in a closed or isolated system of colliding objects. The total momentum is conserved. Now, what does this mean? It means that in a system where there is no external force, okay, note, isolated system or closed system implies that there is no external force. Okay, so that's just what this line means, closed or isolated system. So since there is no external force, it means the total momentum before collision is the same as the total momentum after collision. So let's state it in that way. In a closed or isolated system of colliding objects, the total momentum after collision is equal to the total momentum before the collision. So meaning that when no external force is applied, the momentum, which is product of mass and velocity before the collision of the object, is the same as the product of the mass and velocities after the collision. Let us now look at how we can state this mathematically, and then from there we can now look at the types of collision. The conservation of linear momentum applies the Newton's third law of motion, meaning for objects that will collide, the action and reaction is equal and opposite. So for example, if we take an object A moving in this direction by a force A, and then coming in contact with an object B moving in the opposite direction by a force B. What does this mean? What we see is that after collision or upon collision, A and B, F of A will equal the negative of F of B. Okay? And this is what the Newton's third law of motion states. Action and reaction are equal and opposite. So similar force, they are equal but opposite. That's why I see F of B is negative. Okay? F of A equals negative F of B. Now, what does this mean if we're going to state it mathematically? Now, remember that F of A itself is supposed to be MA, then VA minus UA all over T. And on the other hand, F of B is supposed to be M of B, that is mass of B, final velocity of B minus initial velocity of B, all divided by time T. So now let's apply this and see where it leads us. So we then say MA into VA minus UA over T equals minus MB, because of this negative sign, and then VB minus UB over T. Now, of course, T cancels T. Easy. So now let's open this. We have MA VA minus MA UA. Okay? And this will give you minus MB VB. And then minus times minus will give you plus MB UB. Now there's something you will see here. Okay, we see that u here is negative, but u here is positive. So we want to bring the ones that have u together and the ones that have v together. So if I take this to this other side and relate it with m of b here, now this will become positive, right? So you now have ma ua. This is already positive before, so plus mb ub equals, now on this other side, now I'll bring this negative v to this side so that we have ma va plus mb vb. Now you see, this is what holds whenever you are solving problems on colliding objects by observing the conservation of linear momentum. So do not forget this equation. MAUA plus MBUB equals MAVA plus MBVB. Now, this equation may change depending on the type of collision. So in the case of elastic collision, we have a different equation, and in the case of inelastic collision, there's another equation that we can use. But first, we have to understand what elastic collision is and what inelastic collision is, so that we know why the equation changes, and then we should then be able to apply it to solve questions on colliding objects. Now, don't forget, if you have any question, put them in the comment section and we'll definitely attend to all of your questions. Now, when we say that collision can be elastic or inelastic, now, to understand first what elastic collision means, you have to consider two objects that collide with each other. Now, that kind of collision is said to be elastic on one condition. That is, the kinetic energy of the objects before collision has to be equal to the kinetic energy after collision. So when you have the same kinetic energy before and after collision, then that collision is known as a perfectly elastic collision. Let's put that down. When two objects collide and the kinetic energy before and after collision is the same. The collision is said to be perfectly elastic. Now, let me give you an example of such. Now, when you look at what is known as the pool balls or billiard balls, those that are familiar with pool or what is fondly called snooker. Now, when you hit one of the balls, it goes and then collides with another ball in such a way that the other ball will have its own velocity now, and the initial ball maintains a new velocity. Now, the kinetic energy before collision is the mass of the white ball and its velocity. Now, the kinetic energy after collision becomes the mass of the white ball plus its new velocity, and then you add that to the mass of the ball it hits multiplied by its own velocity. Now, when you add these two, that is MAVA plus MBVB, you have the momentum rather in that case. Remember that kinetic energy is half mv squared. Okay, so when the kinetic energy after collision equals kinetic energy before collision, then what you have there is a perfectly elastic collision. The same thing applies to when you have a ping pong ball now that then hits a hard surface. When you strike it to hit a hard surface, and then it bounces back to the same height from which it was released initially. Just like when you bounce the ball, you release it, it goes down, bounces back to the height it was when you released it, then that kind of collision is elastic. Now, what does that mean? It means that the momentum before and after collision is the same. So in such a way, you have MA UA plus MB UB to equal MA VA plus MB VB. Now, considering the case of the snooker balls now, the other ball that the white ball hits would have a velocity of 0, and if you apply it here, this will give you 0. That's why I said the momentum at that case is that of the white ball. Okay? Now, equals, now the momentum after collision will be the mass of the white ball multiplied by the velocity of the white ball plus the mass of the other ball it hits and then the velocity of the other ball. When you multiply that and then you add the results together, and if what you get on this right hand side of the equation equals what you get on the left hand side of the equation, then that collision is perfectly elastic. Now, if we are looking at it from the side of kinetic energy, what that will mean is that half MA UA squared plus half MB UB squared will equals half MA VA squared plus half MB VB squared. Now, each of these is the kinetic energy of each of the objects with masses MA and MB. So this is what defines the case when a collision is perfectly elastic. Now, let's look at what happens when it is not elastic, that is an inelastic collision. Now that we can describe an elastic collision, let us look at inelastic collision. Now, the difference here is this. For a type of collision, for a collision to be said to be inelastic, it means that the kinetic energy after collision decreases. So if the initial kinetic energy before collision, then after collision it will just be decreased from what you have at the initial. Now, what that means is that the kinetic energy reduces. However, in this case, you must note that the momentum still remains conserved. Because if the momentum were not conserved, then we are not even looking at it. It won't be a problem for us to solve in this case. We are looking at conservation of what? Linear momentum. That is, when two objects collide in such a way that the momentum before and after is the same. So that is why we are looking at the elastic and inelastic collision in line with the law of conservation of linear momentum. So in the first case, for elastic collision, the kinetic energy remains the same and the momentum is conserved. But for inelastic collision, the kinetic energy is reduced, but the momentum remains conserved. Let's put that down. For inelastic collision, the kinetic energy after collision is reduced. However, the momentum is still conserved. Now, what this means is that the momentum before collision and after collision remains the same. Now, one thing you will also note is that for inelastic collision, the two objects after colliding with each other begin to move as a unit in such a way that the final velocity of the object is the same. So, in inelastic collision, the objects move as a unit after collision. Okay? Therefore, V1 equals V2, which we can then call V. So what does this changes from the law of linear momentum that we have studied. So we know that MA UA plus MB UB is supposed to be MA VA plus MB VB. Okay? But VA equals VB, which is basically V. So we can then say MA UA plus MB UB equals, now in this case, what do we have now? We have MA plus MB all multiplied by V, because they will have V in common. Now, if we're going to write this in terms of kinetic energy, we will then say half MA UA plus half MB UB equals half MA plus MB then multiplied by V. So these are the various equations we use when you are told that the collision is inelastic. But when the collision is elastic, you use the equation that we derived in the case of elastic collision. Now let us look at a few questions on the conservation of linear momentum. Here is the question from WAEC 2000. It says, a ball P of mass 0.25 kilograms loses 1/3 of its velocity when it makes a head collision with an identical ball Q at rest. After the collision, Q moves off with a speed of 2 meters per second in the original direction of P. Now we have to calculate the initial velocity of P. Now let's look at what we have in this question and then solve. Now, one thing you immediately see from this question is that you have to assume that it is an elastic collision, because we are not told that the objects move in the same direction or with the same velocity after collision. We are not told that. So since they are not moving with the same velocity after collision, it means that we have to assume that it is an elastic collision. Now, solution. We have M of P to be 0.25 kilograms, which is the same thing as M of Q. Okay? Another thing we have is that initial velocity of P, U of P is unknown, but we know that U of Q is 0. Now, V of P is U of P minus 1/3, 1/3 U of P. And this will give you 2/3 U of P. While V of Q is 2 meters per second. Now, we can now apply M of P, U of P plus M of Q, U of Q equals M of P, V of P plus M of Q, V of Q. But note that this one tends to 0 because U of Q is 0. Okay? So if we apply that, what do we have now? M of P will be 0.25 multiplied by U of P. So 0.25 U of P equals, now, M of P, 0.25, V of P. What is V of P? That is 2/3 U of P. Okay? Plus M of Q, 0.25, multiplied by V of Q, which is 2. Okay? Now, what does this mean? We have 0.25 U subscript P equals, what do we have here? Now, 0.25 multiplied by 2, that's 0.5. Now divided by 3 would give us 0.166. 7 approximately u of p. Plus, now when we multiply this, what do we have? 0.25 times 2 will give us 0.5. Now, what do we do at this point? We collect like terms. Okay, so that is 0.25 u of p minus 0.167 u of p equals 0.5. Now, what's the difference here? Let's see. 0.25 minus 0.167, that will give you 0.083 u of p equals 0.5. So u of p, which is the initial velocity we are asked to find, will then be 0.5 divided by 0.083. And this would give us, that will give us 6.024 meters per second. So there you go. Applying the equation for elastic collision help us to find that the initial velocity of ball P is 6.024 meters per second. Thank you. Now let us solve this question. It says a body P of mass 5 kilograms moving with a velocity of 30 meters per second collides with another body Q moving in the opposite direction at 20 meters per second. Now, if both bodies now move in the direction of P at 10 meters per second, we are to calculate the mass of Q. Now, one thing you have to note from this question is that because velocity is a vector quantity, and we see that the body Q is moving in the opposite direction, the momentum in that case will be a negative momentum. Okay, so when we apply, remember this case now they are moving in the same velocity at the end of the motion. That means that we are applying the case for inelastic collision. Now that means m of p u of p plus m of q u of q is supposed to be mp plus mq all multiplied by v. Except that in this case, but note that m of q, u of q is negative. Okay? Because it is in the reverse direction. So that will change this sign here. So that is m of p, u of p will now be minus m of q, u of q, which is equals to m of p plus m of q, then v. Okay, since they are in reverse directions. Now, let's apply what we have. M of p is 5, multiplied by initial velocity, which is 30, minus m of q times 20 equals 5 plus m of q all multiplied by v, which is 10. Right? So now let's see what happens here. This will give us 150 minus 20 m of q. And then this will give us 5 times this, that will give us 50 plus 10 m of q. Now let's continue here. When we collect like terms, collecting like terms, we'll see that 150 minus 50 equals 10 m of q. Then this comes here and becomes positive 20 m of q. Now when you add this, we have 30 m of q equals 100. Now dividing both sides by 30, we see that the mass of object q will then be, now 0 cancels 0, 3 goes here 3 times, remember 1, so that's 0.33. And that will be in kilograms. So the mass of object Q is 3.33 kilograms. And that's the solution to this question. This question from the WAEC of 2003 says, a tractor of mass 5.0 times 10 raised per 3 kilograms. In fact, to keep it simple, I'll just give you in normal form. This means 5,000 kilograms is used to tow a car of mass. This would be 2,500 kilograms in normal form. Now, the tractor moved with a speed of 3 meters per second just before the towing rope became taut. Now, we are to calculate the speed of the tractor immediately the rope becomes taut, and then 2, the loss in kinetic energy of the system just after the car started moving. And then the third part is to find the impulse in the rope when the car jerks into motion. So let me divide this into 3 so that we solve them individually. Now, starting with the first part. Okay? Now, we see that this is a case of inelastic collision in the sense that after the rope becomes taut, the two objects are going to move in the same direction with the same velocity. Okay? So what we are going to be applying is m1 u1 plus m2 u2 equals m1 plus m2 all multiplied by v. Now, it is this v we are asked to find. Okay, the speed of the tractor immediately the rope becomes taut. That is the final velocity. So let's solve. M1, mass of tractor, that will be 5,000 multiplied by the initial velocity of the tractor, that is 3, plus mass of the car, 2,500 multiplied by the initial velocity of the car, that is 0, equals, now we have 5,000 plus 2,500 all multiplied by v. Now, what does this give us? This is 15,000 equals 7,500 v. So the final velocity v becomes 15,000 divided by 7,500, and that will give us 2.0 meter per second. That's for the first part. Yeah. So now let's solve the second part. Now we have to find the loss in kinetic energy of the system. Okay? Now, the initial kinetic energy, remember that in this case is an inelastic collision. So the kinetic energy is supposed to reduce after the collision, or in this case, after the rope becomes taut. So before the rope becomes taut, let's find the kinetic energy. That will be half m1 u1 squared plus half m2 u2 squared. So what does this give us? This is 1 over 2 times 5,000 times 3 squared plus 1 over 2 times 2,500 times 0 squared. Now all of this tends to 0. So we are left with this, which is 5,000 times 9. Okay? Now 5,000 times 9. 5 times 9 would give us 45. Okay, so 45,000 divided by 2, and that will give us what? Divided by 2, and we have 22,500 joules as the initial kinetic energy. Now the final kinetic energy would be half m1 plus m2 v. That is, we have 1 over 2 into 5,000 plus 2,500 all multiplied by 2. Remember, v squared, so 2 squared. So from here, 2 here takes out one of these, so we are left with 2 here. And then what we have here is 5,000 plus 2,500, that will give you 7,500 multiplied by 2. And what do we have? That is 15,000 joules. So the loss in kinetic energy would then be 22,500 joules minus 15,000 joules. And what does that give us? That will give us 7,500 joules. That's for the second part. So now we've been able to solve the first part. We got 2 meters per second. The second part, 7,500 joules. Now let's solve the third part. The third part of the question asks us to find the impulse in the rope when the car jerks forward. Now remember, impulse is supposed to be force times time, or change in momentum. Okay? So if that's the case, we're going to use the change in momentum part since we don't have a value for force in this question. So the impulse would then be, now we'll be using the mass of the car because that's what we are asked to do. The impulse in the rope as the car jerks forward. So mass of car, that's m2. Okay? V minus m2 u of 2. Remember that this is 0, right? So if this is 0, that is the impulse becomes m2v, which is basically the mass of the car, 2,500, multiplied by the velocity, which is 2. That is the final velocity. So the impulse there is therefore 5,000, and it is in Newton seconds. So the solution to this question, the first part is 2.0 meter per second. The second part is 7,500 joules. And then the final part is 5,000 Newton second. Now, I encourage you to practice with even more questions on the conservation of linear momentum. Now, don't forget that we are always here for you. So during your practice, if you come across any question that is challenging and you would like some help with that, please put the question in the comment section, and we promise to attend to all of your comments. Thank you so much. We continue on our study of linear momentum. Let's talk about the applications of the Newton's and conservation of momentum laws. Now, you already know from the last thing we discussed in this video, we talked about the conservation of linear momentum. And we looked at when the collision is elastic, that is perfectly elastic, and when it is inelastic. Now, you recall that when we were talking about that, I did mention that it takes its equation from the Newton's third law of motion. You recall when I mentioned something like this, when you have an object A and then an object B. This one moving with f of A and this moving with f of B. And then I said f of A equals negative f of B. You see that? That is where they both link up, okay? So now let's see how this is applied using examples that are relatable. Now, the first application we want to talk about is in the recoil of a gun. Recoil of a gun. Now, personally, I have never shot a gun, so I cannot tell you exactly how it feels because I've never felt it. Okay, so most of the experience I know about shooting of gun and the recoil are from things that I see either on screen or some of the things that I've seen live also, because I've been to places, the military barracks, where I've seen soldiers actually shoot guns. I've been to events where they do the 24 gun salute amongst other things, and they shoot rifles. I've seen those things happen, but I've personally not held a gun, neither have I ever shot a gun. Okay, but there's this scene that always comes to mind whenever I'm trying to talk about the recoil of a gun. It's from an old movie. I can't remember the title now. So if you do know the title of this movie, feel free to put it in the comment section. So, but what I remember from the movie is this. There's this guy. They were fighting against aliens. They were working against aliens. Some were protecting the aliens while some were trying to arrest the aliens and things like that. I can't really say what was really going on there. But this new recruit was going to be given a gun so that they go in battle. Now, when they opened the chamber where the guns were, the person who recruited him gave him a very tiny weapon, a small gun, and he was really angry about it until he got to the field of battle and had to shoot from that tiny gun. And the moment he shot, the recoil was so much that it was thrown away and it landed on a car. I can't forget that scene, really funny. Because you don't expect such a small gun to pack such an amount of recoil. Okay? Now, what recoil there means is this. Now, you see, when you are about to shoot a gun, the gun itself has zero velocity. Okay? But the moment you shoot the gun, the bullet comes out of the chamber and goes at a very high speed. Okay? Now, recall, initial velocity of the gun is 0. But the mass of the gun is large. Now, the mass of the bullet is extremely small, but the velocity is very high. But if conservation of momentum occurs in this case, since it's going to occur, now what will happen is that the gun will shoot backwards as the bullet is fired forward. Okay, the difference now is that since it is conserved, the mass of the gun itself is large compared to the mass of the bullet. that would give you something whereby you see that the momentum there is going to be very close to that of the bullet as it is fired. And by the time you sum them up, it will give you the initial momentum. I hope you understand what I'm saying here. So basically what I'm saying is when you fire the gun, the bullet at initial, you'll be looking at mass of bullet multiplied by velocity of bullet. And this would give you mass of gun plus mass of bullets and then velocity. You see this velocity here is how you get the velocity of the gun, that is the recoil of the gun. Is that clear now? So in this case, you can find the velocity of the gun, the velocity at which the gun is going to move backwards. Let me give you a question where we apply this. Okay, let's say calculate the recoil velocity of a gun of mass 20 kilogram if it shoots a bullet of mass 50 grams at velocity of 200 meters per second. So you see here we have the mass of the gun, we have the mass of the bullet and the initial velocity of the bullet. Remember that the initial velocity of the gun is 0. So at this point now we can then find the recoil velocity. So this is what you do. Remember, mass of bullet, the mass of bullet is 50 grams and that will be 50 divided by 1000 to bring it to kilogram. That will give you 0.05 multiplied by 200. All of this equals 0.05 plus 20 all multiplied by V. Now if you want to solve this easily without calculator, it would be better to put this in fraction. So that would be 5 over 100 times 200 equals, now this is 20 plus 5 over 100 all multiplied by V. Now you see, this goes here, giving you 2 there. Okay, now when we work with this, 5 times 2 will give you 10. 10 equals, when you multiply this, you get 20V plus, remember this is 5 here 1, 5 here is 20. So that will V over 20. Okay, now when you add this up, what do we get? Now let me continue at this stage here. We now have 10 equals, now take LCM here, that will give you 20. Okay, this is over 1. Okay, 1 here 20, 20 times 20V will give you 400V plus V. And then when you cross multiply, you have 20 times 10. 20 times 10 will give us 200 equals, now when you add this, you have 401V. So to get V, you just do 401 divided by 200. And what would this give us? That will give you 2 points. Now that's 1 over 2. 1 over 200, that will give you 0. Let's do that here. 1 over 200. 0 point, okay, 0, 0, 5. Okay, so 0.005. So our answer is 2.005 meter per second. Now in reality, the recoil velocity of a gun is usually not this much. Okay, but this is a question that I just put out to just practice using this equation. Right, so at no point would you see guns that usually give you this kind of recoil, except if you are talking about RPGs among other types of ballistic missiles. Okay, but what we are learning from this is that these applications, these laws of linear momentum, conservation of linear momentum, as well as the third law of motion, is applied even when you shoot missiles, guns, amongst other type of ballistic materials or weapons like this. It all applies the law of motion as well as linear momentum. You recall that we mentioned the law of conservation of linear momentum, and also we have stated the laws of motion from the first, second, and third law. Now you see that when we're talking about the conservation of linear momentum, I did mention that when you have an object A and object B moving in opposite direction like this, they then collide. This moves with a force F of A, this moves with force F of B. And we mentioned that F of A is equals to the negative of F of B. And this is taken from the third law of motion, which says that to every action there is an equal and opposite reaction. Or we just say action and reaction are equal and opposite. Now what we want to do is to consider some of the applications of the Newton's and conservation of momentum laws. Now, the first application we're going to consider here is in the recoil of guns. Recoil of guns. Okay? Now, personally, I have never shot a gun. I don't know what it feels like when you shoot a gun, but I have seen places where guns were shot. I've been to events where you see the military performing what is known as the 24 gun salute, amongst other things like where they raise their gun and then shoot into the air. I've also been to the police barracks, the military barracks as well, and I've witnessed where soldiers actually shoot from their rifles. But I have not felt what it is like when you shoot. I don't think I want to experience it. I don't think so, okay? But there's a scene that usually comes to mind whenever I'm trying to explain the recoil of a gun. Now, it comes from a very old movie. Now, I don't know if you've seen that movie before, but let me just narrate what that scene looks like. Now, in that scene, the movie is about this secret organization that always goes around looking for aliens. Because in that movie, aliens and humans are able to interact, work on Earth, do things together, and sometimes the humans don't even know that they are interacting with aliens. So there's this secret organization where they go out, look for aliens, and then gather them around. Now, in this particular scene, there's a recruit that was supposed to join another person, an experienced person, to go out to look for aliens. And then at that point, he was to be given a weapon. When the weapon vault was opened, he was happy because he saw a lot of big weapons there that he was interested to handle. But his handler only gave him very small weapon, a very small pistol like that. And he got angry about it, but didn't know what he was holding until he got into the mission field. Now, while on the field, he shot from this gun and then something happened. The moment he aimed and fired, he was jerked back at such a force that he landed on a car and broke the windshield of that car. Now, you see that thing that happens where he shot the weapon and then was thrown back is as a result of the reaction that you get when you shoot. Remember, the bullet goes forward, that is the action. There is what? An equal and opposite what? Reaction. That was why he was jerked back and hit the car. So you can imagine the velocity at which he was thrown for him to be able to hit a car and then destroy the entire windshield of that car. What you see there is recoil of a gun in action. Now, in reality, it doesn't happen like this. Now, this is because the mass of the guns we shoot, that soldiers and others use, compared to the mass of the bullet, is significantly different. The mass of the gun is large, while the mass of the bullet is small. And even in cases where you are using tanks and the likes to shoot bigger warheads and things like that, you still see that the mass of the weapon itself is significantly larger than the mass of the bullet or whatsoever device that is inside that it is shooting out, which is why the recoil is often not of high velocity. Okay, but they still apply the Newton's third law of motion. To every action, there is an equal and opposite reaction. And as well, it follows the conservation of linear momentum because the momentum of the gun and the momentum of the bullet is conserved. Okay, so when they are conserved, what does that mean? It means when you shoot from your gun, let's say the mass of bullets mass of bullet equals m1, and then velocity of bullet equals v1. Then the mass of gun, let's call that m2, and then velocity of gun, let's call that v2. For this law to hold, it means that m1 v1 plus m2 v2 should give you 0 if it is conserved. And what this implies is that m1 v1 equals negative m2 v2. Now this is because before the bullet itself is fired, the momentum of the gun and bullet is 0. Okay, so we can then apply this to find the velocity, that is the recoil velocity of a gun. Let's take an example so that you see how we apply this in physics. So let's say a gun of mass 20 kilogram shoots a bullet of mass 50 grams, and the bullet is fired at a velocity of 200 meters per second. Let's find the recoil velocity. Then put down the question. Example: find the recoil velocity of a gun of mass 20 kilograms if a bullet of 50 grams is fired from it at 200 meters per second. So applying this equation, what will we get? Mass of bullet, velocity of bullet equals negative mass of gun, velocity of gun. So let's apply it. So mass of the bullet is 50 grams, okay? 50 grams is 0.05 kilograms. Multiply that by the velocity of the bullet, which is 200 meters per second. Now this equals negative mass of gun, 20 kilograms, multiplied by the velocity, which we do not know, okay? So when you multiply this, you get 10. 10 equals negative 20v, which means the velocity, the recoil velocity is 10 over negative 20, which will give you negative 0.5. Now, the negative here only shows you that it is going in the opposite direction, okay? The actual velocity is therefore 0.5 meter per second. Meaning if you shoot from this gun, it will jerk back at a speed of 0.5 meter per second. I hope you understand how it is applied now. So this is just one of the applications of the Newton's and conservation of momentum laws. Let's look at some more applications of these laws. Another application of the Newton's and conservation of momentum laws is in the propulsion of rockets. So rocket propulsion. Have you ever wondered how is it that we're able to create aircraft amongst other things such that they defy gravity in such a way? They don't necessarily defy gravity the way we think they do. What they do is they apply the Newton's law and the law of conservation of linear momentum. As long as it obeys this, it will fly. I mean, just consider, for example, a balloon that is inflated. Now, when you inflate a balloon, pardon my diagram, okay? And then for some reason, you pop the balloon at this point. What is going to happen? You will see that the balloon will begin to move like so. Okay, why? Because the air here begins to come out. So depending on the direction of the air, the balloon will move in the opposite direction. Why? Because it is going to obey the Newton's third law of motion. To every action, there is an equal and opposite reaction. Air is let out, which is going downwards, and as such, the reaction will be to pull the balloon upwards. That's why when you burst the balloon, it begins to fly about. Now, this is the same principle that rockets use. especially rockets that launch satellites, they always ensure that, you see, they have this chamber where they burn fuel. Now, as it burns fuel, it is going to release hot gas at a very fast rate. Now, the reaction to that ends up in the rocket itself being lifted, and then it begins to fly as it goes, like that. And it goes at such a velocity that it's able to escape Earth's gravitational pull. The same thing applies to airplanes, jets, and the likes. What happens is that they let out hot gas and then they fly in the opposite direction. As simple as that. Just follows the law. Okay? So if you're going to find out, this is why you see that jets sometimes are built with materials that are light, so that it will be able to fly by letting out the minimal amount of gas. What you need is how fast it burns fuel, okay, and then with that and the velocity at which the gas is going to be ejected from it will help you know the maximum weight that jet engine or that jet in total will be able to be. So with that calculation, that simple calculation, you can know the maximum weight you can make a jet if you really want it to fly. Let me put this together for you. Now, let's say, for example, if a jet burns fuel at 200 grams per second and releases hot gas at 400 meters per second. That is, the velocity of the gas that is released at the end of the engine is 400 meters per second. Calculate the max weight of the jet. So when we're going to solve this now, all we need to do is remember that the weight is the same thing as force, and all we need to do is the product of the rate at which it burns fuel and the velocity of the gas it releases. Now, this has to be converted to kilogram per second, so that means we divide it by 1000. That will be 200 over 1000 kilogram per second multiplied by the velocity, which is 400 meters per second. Now look at this. 0 cancel 0, 0 cancel 0, 0 cancel 0. So we have this equals 2 times 40. That will give you 80 kilogram meter. You know, this per second, that gives you per second squared. Okay? So at this point, what do we have? That is 80 newtons. The maximum weight of this jet has to be 80 newtons. So by applying this calculation, you can always find the mass of the weight of an aircraft, depending on how fast it burns fuel and the velocity at which the gas is released. So this will be the second application for which we are looking at the applications of Newton's and conservation of linear momentum laws. Now let's move to another application. Let us consider another application of Newton's and conservation of momentum laws. Okay, now this one would be in why walking is possible. Now, when a person walks, what really happens? Okay, now, I'm not very good at drawing, so pardon me, I'll just draw a stick man here at this point. Okay, now, he has his leg like this, okay? Okay, now this will be the forward leg, then this will be the one at the back. Now, what do you see is happening at this point? Okay, you see that as he's moving forward, he pushes on the ground with the leg that is at the back. Okay, as you can see here, this leg pushes on the ground. which means the action is to push backwards. Now, what will be the reaction? Action is what? Push backwards. Now, the reaction, moving forward. Okay, and this is what we continue to do that makes walking possible. You continue to push backward with one leg, making you move the opposite direction. Remember, to every action there is an equal and opposite reaction. So as he pushes on the earth downwards, it propels him forward, and it continues like that, and is able to walk from one point to another. It all follows the application of the third law of motion and the conservation of linear momentum. Now, at this point, it's important that I mention that of all the three applications we have talked about, from the recoil of a gun to the propulsion of rockets, jet engines, and the likes, to the walking of man, other contributing factors are there, such as friction, air resistance, amongst the rest. Okay, but that is to let you know that in all of these cases you don't have elastic collisions. There are cases of what? Inelastic collisions. There are also cases of elastic collisions, but the applications you have considered look at inelastic collisions, because there are other things that will reduce the kinetic energy in the reaction part. Okay, so since the reaction part is going to, the kinetic energy at that point is going to be reduced, what that means is that whenever you are creating things like this, you always have to factor it in. For example, because of friction, you have to apply more force when you are walking, and you also have to know that it is friction that is making us to be able to stop. Otherwise, the moment you just push, according to the law of inertia, you will continue to move at the same velocity in the same direction. But because of friction, you are able to stop, continue, move, continue, and like that till you get to your final destination where you put a stop to it. The same thing applies to the jet engines. You see that it's able to move as long as it is pushing out air, and it has to throw out more energy for it to be able to break air resistance and friction with the other things that are factored in that case. The same thing also happens in the case of recoil of a gun. You always have to factor every other thing from friction to air resistance and the likes. Okay, but it does not take away the fact that linear momentum is conserved in all those three cases. Now, what I would like you to do is go to the comment section and then drop in the comment section any other applications of the Newton's law and the conservation of linear momentum that you know. The next thing we need to learn under the conservation of linear momentum is inertial mass and wave. Now, before now, you define mass, we often define mass as the quantity of matter contained in an object or a body. Okay, but we have seen that every object wants to continue to move at the same velocity it is, or remain at its rest position, okay, provided that an external force is not applied. And we define that as inertia. That is the tendency of a body to want to remain stationary or to move with the same velocity, that is constant velocity in the same direction. Okay, now this means that inertia is actually an inherent property of mass. That is, you can't separate them. Mass and inertia are, they depend on each other. That is, you cannot talk about mass without talking about inertia. This leads to a new definition for mass as the quantitative amount of inertia that a body has. Okay, that is the quantitative measurement of the inertia a body has. Let's put that down. Mass can be defined as the quantitative measure of inertia of a body. Now, what this helps us to agree on is the fact that the larger the mass of a body, the more inertia it possesses. Okay, remember when we're talking about the Newton's first law, otherwise known as the law of inertia, I did mention that when you have a large object, it becomes difficult for you to push it. This is because it has a high amount of inertia as compared to a body with less mass. Okay, so that is when we are talking about inertial mass, we are looking at a body's resistance to the force applied, no matter the amount of force we are talking about. Okay, so if you're asked to define what inertial mass is, this is what you should say. Inertial mass refers to a body's resistance to force applied on it. So the amount of resistance that a body is going to give to the force applied on it is what we know as the inertial mass. Okay, now this gives rise to our understanding of what weight is. Okay, this is why when we want to measure weight, we see it as the effect of gravitational pull on an object of known mass. So this is why we say weight is a product of mass and gravitational acceleration. Now, this is because the body itself is resisting the application of a force, and this is as a result of the Earth's gravity pulling it towards its core. So to find the weight of an object, you have to multiply the mass and the gravitational pull. So the equation there says weight W equals mg. Don't forget, weight is W, so W denotes weight, m denotes mass, and then g denotes gravitational acceleration. Gravitational acceleration. Okay, now let's apply this to understand weight whenever it's in a lift, or what we know as an elevator, when it is stationary, when it is moving upward, when it is moving downward, and when it is falling freely under gravity. Let us now consider the weight of a body in a lift. Now, we already know that the weight of a body is the product of mass times gravitational acceleration. But what happens when you put it in a lift? Does it change? Now, to understand this, we're going to look at 4 different conditions. The first condition we are looking at is when the lift is stationary. So that it is not moving. Okay, now in case you don't understand what a lift is, we are looking at an elevator. They are the same thing. Okay, so this is that machine that helps you move from one floor to another on a tall building. Now when you are in that lift and it is stationary, that is, it's neither moving upwards nor downwards, what do you observe there? You see that acceleration itself equals 0. Now please note this, depending on the direction of the motion. Okay, you see what you know as F equals ma. This a here would be the acceleration of, as in the effective acceleration of the object in the lift. Now effective acceleration is this. See, look at this. Effective acceleration. Acceleration depends. If the object is moving upward, in the case of upward motion, you have A1 plus A2 to give you the effective acceleration. Now, when it is moving downwards, it would be A1 minus A2 to give you A. Okay? So, now when it is stationary, we can choose to use either plus or minus. Remember, acceleration is 0. So force equals weight, which in this case is mass into A minus or plus G. Let's use plus G. Okay? So in this case, what do we have? It means we have mass into 0 plus G. That is, the weight is mass times gravity. Because when you add this, it is just G. And G times M remains mg. So when the lift is stationary, the weight of any object measured in it remains the same. Mass times gravitational pull. Now let's look at what happens when the lift is accelerating upward, okay? When it begins to move upward at an acceleration A. Let's look at what happens to the weight at that point. Now let us consider what happens when the lift accelerates upwards at an acceleration A. Okay? Now, when the lift is moving upward, the effective acceleration becomes A plus gravitational acceleration. Because gravitational acceleration is pulling it downwards while it is accelerating upwards. And when you look at relative velocity, in this case, you're supposed to add them together. The same thing affects acceleration. So you add them together. That will mean weight. Let's call this W1. Since we've used W for when the lift is stationary, this is condition B. Okay? So now W1 would then be the mass multiplied by A plus G, where A is the acceleration of the lift as it moves upward. Now, one thing we can agree here is that W1 is definitely greater than the original weight of the object. So whenever you are in a lift that is accelerating upward, you should feel that you are a little bit more heavier than you are. That is, you feel a little bit more weight on yourself. You feel heavier as compared to your original weight. That's why we have it here as W1 is greater than W. Now let us consider when the lift accelerates downward at an acceleration A. Okay, so in this point now we are saying that the lift is coming downwards. Now what this means is that the resultant acceleration or effective acceleration becomes G minus A. It can also be A minus G depending on which one is greater. Okay, so when the lift begins to accelerate downward, there is a reduced effective acceleration on the object in the lift, which will mean that the weight, now since we've used W and then W1, I'll then call this weight 2, would therefore be the product of mass and what we have here, which is effective or resultant acceleration G minus A. Now this will give you a lesser acceleration, so as a result we can now say that W is greater than W2, or we can say W2 is less than W. What this means is that a person will feel lighter when he is in a lift that is accelerating downwards. Now don't forget, when the lift is stationary, you have your original weight. As the lift accelerates upward, you feel heavier, that is, the weight increases. Now when the lift begins to accelerate downward, your weight reduces. Now let's look at the fourth case, which is when the lift cuts and then it begins to fall freely under gravity. In the case where a lift should cut and then begins to fall freely under gravity, let us look at what happens to the weight of the object in the lift. Now, when it is falling freely under gravity, this means that the acceleration A equals G. Okay? And weight 3 would then be M. Remember, it is moving downward, so G minus A. That is, weight 3 therefore becomes M into G minus. Now, instead of A here, I then put G because they are the same now. Okay? So W3 therefore becomes M into, this will give you 0. So that is the weight of an object in a lift that is falling freely under gravity is 0. So this is a case of weightlessness. weightlessness. So if a person is in an elevator or any object that is moving vertically downward freely under gravity, such a person should feel weightless at this point. Now, this will prompt us to begin to consider what weightlessness is, especially when it comes to satellites. Now, when we shoot satellites into outer space, they begin to orbit around the Earth. Let us look at what really makes it go around the Earth the way it does, and then we'll also look at what happens to people that are in the International Space Station. There is this common saying where they say that in outer space, there is no gravity. And then they always show this to us, especially in movies amongst other things like that, where we see astronauts in space and we see them floating. Now, they say this is because there is no gravity in space. Let's see if this is true. Now, consider a satellite that is put on a rocket and then shot into outer space. What really happens? Now, let's take this to be the Earth. Now, it's not a perfect sphere, so I think I did okay with this drawing. That's just me saying something there. Now, let's say this is the point where the satellite, the rocket, is shot from. Now, as it goes up like this, what happens? By the time it gets into space, it begins to move sideways like this at very high velocity. Okay? Now, at the same time, Earth's gravity begins to pull it towards the core. Okay? Gravitational pull. Now, you remember that when you have two vectors now acting at an angle, what will happen? There's always a resultant vector, right? So as a result, it pushes the satellite to move along an elliptical curve like so. Now, as that continues, it continues to try to move forward while gravity continues to pull it, and that will cause it to continue to move like this. And then as it goes again, it moves like this. So what's basically happening here? You see that the satellite is falling around the Earth. As a result of these two forces, one being the one propelling the rocket itself to move sideways, and then the other being gravitational pull of the Earth, which is also a very large amount of force. Okay, so because of this, it begins to fall around the Earth. Now, this is something you should know. In outer space, there isn't really a up or down. So even when it gets to this point where it is moving like this, in my diagram, it appears as if it is moving upward. But in outer space, the feeling is the same. It is falling freely under gravity. And when something is falling freely under gravity, what happens to the weight? Remember, the weight becomes mass times gravity minus the acceleration becomes gravity also, and this will give you 0. Hence, weightlessness is felt. Weightlessness. And when something is weightless, what will happen? It begins to float. You see this now? So because it is falling freely under gravity and moving around the Earth like that as a result of that gravitational fall, is why you feel weightless in the International Space Station. Not because there is no gravity. There is gravity, but the rocket or the station itself is moving at a velocity that counterbalances that of the Earth's gravitational pull. And as a result, it begins to fall freely under gravity, because what you feel there is weightlessness. I believe now you understand why astronauts in space float. It's not because there's no gravity, but because it so counterbalances each other in such a way that the person begins to fall freely under the effect of gravitational pull. Now, don't forget that if there's any question at all you have considering what we have done so far, or even if it is during your study time you came across something that you need some help with, we are always here for you. Remember, we are your flawless school too. So no matter what you need, ensure that you put it in the comment section, and we promise to attend to all of your comments. Now folks, please don't forget to subscribe to the channel if you are yet to be subscribed. Kindly take a moment of your time, click the subscribe button, and also click the notification bell icon. Now what this does is that every time we put out a new content, you will always be notified. So that way you don't get to miss the amazing educational stuff that we are putting out here on our channel. And please help us to reach many others like you who need helpful content like this by sharing our videos. Ensure that you share the video and ask them to also interact with our video. Drop a like, drop a comment. We are always here to make sure that your academic journey is interesting and also rewarding at the same time. Thank you so much for following the video so far. We still have very much more to come your way, so ensure that you click the subscribe button and the notification bell icon so that you don't get to miss the next awesome video that is coming your way. Thank you so much. Bye for now.